Hey, how's it going, guys? So here we are back again, doing this Open-FDD vibe coding experiment with a Streamlit application. The code is living here in the Python BACnet X playground. It's a vibe coded app, but I think I finally have something to show you guys. The last couple videos have just been um, the process of myself like vibe coding in Cursor on how to make some basic fault detection equations in Python. Um, so I'll try and cover this in an hour and then also completely go over one building as fast as I can with this Streamlit application. So just for starters, the fault detection equations live in the Open-FDD repository, which these lessons learned from here will eventually get uh, incorporated into the Open-FDD project, which is going much slower than I anticipated. It's just application that's written in Rust. So prototyping in Python is really fast. As you can see, the last 10 videos or so, it's pretty quick for prototyping an application, pushing it along with the AI IDE, and then Python, good prototyping language. All of this will be ported over into Rust, which is more, it's not friendly for a prototyping language, but it's a really heavy duty application, systems level kind of a programming language. It's compiled. So Python is a scripting language. It's compiled at runtime. It's works really well with doing things fast with AI, vibe coding, and then as soon as we can kind of fine tune some of these ideas that are working well in Python and prototyping, we can we can port that all over to Open-FDD and Rust, which I'll show you how to do that too. So that's going to be maybe another video. Maybe I could do that tomorrow, but that'll be like a loop engineering. So I'm going to ask probably ChatGPT Soul to create a massive loop for cursor agents to iterate how the Streamlit application was built in Python, and then that'll become ported over to Rust. Things will be a little bit different, but it'll I want it to be the same look and feel. Only on the Rust, we'll use SQL instead of Python for the fault equations, which I'll explain that here. So these are the rule library in the Open-FDD docs online, the online documentation that's made by GitHub. So GitHub can make you a website basically based off of uh, your markdown files documentation in your GitHub account. So let me know if you ever want to walk through on how to do this as well. It's kind of cool. GitHub can make all this for you. So all of the rules here, all 50 rules are written in Python. So we've talked about this before. This is ported over into this uh, Python data science application called Streamlit. So I think we talked about this yesterday. So is a Streamlit is like Python. It's basically a dashboarding application. So it's really neat for data scientists and analysts to be able to quickly spin up a web app, which then you could stick on the internet and then be like, hey, look at these are your results. So, which is kind of a concept that works really good for fault detection too. So, if you were crunching a lot of numbers for um, data for your clients, Streamlit is really good for that. It's not a full-blown web application like we talked about before. Like a software engineer wouldn't use Streamlit, but an analyst would, or a data scientist would, because you don't have to do all of the full back end web app framework, any of the front end. As you can see right here, this there's Python code that it behind the scenes it turns it into front end. Um, so it's pretty cool. So that's the power of Streamlit. I think I've even seen people make a Streamlit app with Open-FDD on like some of the really old legacy stuff. So it's you know, it's happened before. So dash plotly. This is another application to do this as well in Dash. You can spin up like really fast dashboards all in Python without having to know JavaScript and HTML. Okay, so anyways, so I talked about where the rules live, the rule cookbook on Open-FDD documentation, and then this vibe coding app lives in Python BACnet X Playground, and vibe code app 19 in here. This is the Streamlit app, and it's also published as a GitHub package. So you can do just a Docker pull, which I'll demonstrate here in just a couple minutes how that works. But I'll be publishing updates. I've been publishing lots of updates, as we need them. And then you just do Docker pull latest. This will be future Open-FDD style of installing Open-FDD when it's ready. And then it's also supported on so Raspberry Pi. You would do this, and then normal x86. You would do this Docker image. So we can make two Docker images, one specifically for Raspberry Pi's ARM 64, or I think this would be a Mac as well, and then just like Windows computers, you'd be using this. So just to show you how that's built real quick too. Whoops, that didn't work. So just to show you how that's built real quick, this is a GitHub workflow. So GitHub Actions, it's this guy right here, is when I push code back to my GitHub, this is a triggered workflow, and AI can set all this up for you really easily too. So you don't have to worry about like, oh my God, I'm never going to be able to learn all this stuff. Like Cursor can just set this up for you. Or it can set up how to build all of those GitHub pages that I showed you of the expression rule cookbook. AI basically wrote all that. So this is what it does. So like it spins up a little Linux image on the cloud, and then it uses this program called QEMU to build Linux images of different architectures. So like I can do, this is how I can spin up without having a Raspberry Pi, I can push a Raspberry Pi image, ARM 64, and then also do x86 all up on GitHub Actions, and you can pull the Docker image down. Which is all possible through this GitHub Actions here in QEMU. It's kind of a cool program. Okay, so like if I go just into the vibe code app 19 here, there's some more information here as well. So like, the expression rule cookbook and pandas. So like what I wanted to cover was just this, how to do this in Docker. I can probably demo this too in PowerShell on Docker Desktop in Windows, but so I'm just going to bring up PowerShell here. And like I showed you yesterday, anyone doing this on Windows, you download this from Windows App Store, Windows Terminal. Download this guy, and this is really cool app. I love Windows Terminal. It, like to me, it makes it like a mirror of what Linux Terminal would look like. So then I'm just going to SSH into my other Linux instance, my little computer right next to me that I've shown a few times. It's called Ben's Bench at the moment. So this is just a Ubuntu server running, so there's no desktop environment. It's just through SSH terminal. Nothing going on very much at the moment. It's not a lot of RAM or anything either. It's just an old repurposed desktop, which I personally love doing. Is if you ever want to experiment, just go to your local computer store and buy a refurbished, um, like a mini slim or something like that. It's probably way more cheaper than buying a brand new Raspberry Pi at the moment. Plus, it keeps your local computer store in business. You know, they like it too. So it's good to keep your local economy running. Plus, like, I never really need a Raspberry Pi either. Like, I have demonstrated once where I've wired a sensor into the Raspberry Pi, the GPIO. I had a one that in front of me, like a one wire temperature sensor that I could wire right into the Raspberry Pi, and they have some electrical input um, terminals called GPIO. So the Raspberry Pi is really good for prototyping electronics, but that's like really rare that I'm actually wiring something directly to the Raspberry Pi. I'm always 99.9% of the time is using a Linux environment to network requests to other devices that are already measuring the environment, like BACnet devices. So that's, I just never need the GPIO of a Raspberry Pi, and plus they're really expensive at the moment too. So some old mini slim computer, 16 gigs of RAM, if it has like a terabyte solid state drive, that's awesome. Raspberry Pis don't come with solid state drives. So if I repurpose an old desktop computer, I have a solid state drive. I don't have to worry about SD card burnout because I'm usually only network requesting data and then I'm saving data locally. So with the solid state drive, I don't have to worry about SD card burnout, which can happen. Okay, so where are we? We're on the Linux computer. Let's do a clear. Whoops, a clear. So I have Docker installed on here already, and good old Windows terminal. So I'm just going to copy this right here. This is going to um, pull the latest Docker container that I showed you, and then stop any previous ones, and then it's going to run it. That's how easy. That's the power of Docker. So like if you were, what's also really powerful about this too is that if you were, let's say you manage a lot of buildings and you have an office in the buildings that you're managing, and it's like a campus environment or something like that, and then you could even have the IT department spin up a virtual machine for you. And then as long as you could just you just aim them, tell them right here, like, do, spin this up, spin up Ubuntu server instance on a virtual machine. This should be completely free, and just there you go. This is what it'll do. So like, if they're really hesitant on the software, they could even scan the GitHub repo for security vulnerabilities. Um, and we could even move this to um, its own repository too. I have a feeling like I kind of want to keep it in this vibe coding thing because I'm going to port all this over to Open-FDD in time, and it'll be rewritten in Rust. So until then, but this step will be this exact same. So what it's doing right now is it's pulling the images from GitHub. Okay, so I do have a I do have this old see, so Docker PS. I think I have an old instance of it running. So I'm just gonna do Docker stop. So this is what you do if you have an old instance of it's running and you want to update it. Let's just repaste all this in. Oops. Okay. Okay, so it already pulled the image. Okay, so there it is. So then we can just go to, we can dial into it. So I just have to dial into this guy and here. Okay, so this is the latest Streamlit application from online. I think I showed you a little bit of the last couple of videos of Streamlit. So like basically I'll demonstrate this on the next building, but you'll have like, so this is my weather data. Basically I have weather data downloaded from openmedio.com, and then this is this building 100 data set. So it's just a pretty typical load zips, pretty typical building automation data, you know, that kind of thing. It's HVAC, all the air handling unit data, all of the central plant data, VAV boxes as much as I can. And then also weather data from openmedio.com. And then behind the scenes, the Python code merges those data sets together and crunches a ton of numbers and analytics for us. Okay, so I'll be able to download that here. Okay, so like right away, we can see with this data that it starts, this is the first time stamp, is March 16th, and the last time stamp is 3rd of July, 2000 hours. And then these are some settings that I want to do for a zone comfort, high and low. So this is like what happens behind the scenes. We talked about this before. It's like per the tenants, per the landlord's requirements for the tenants in their lease agreement, they have to maintain 72 degrees during these hours from 6 to 5, Monday through Friday. And then again on Saturday, so I can just check this box on Saturday, they have to maintain 7 to 1400. So that's 7 to 2 on Saturday, closed on Sunday. And then the rest of the time, they could be shutting equipment down, and temperatures can drift for energy savings purposes. So we talked about this the last video. This is run hours per week of the airside systems. The lowest hanging fruit in energy management is not running equipment more than you have to. So there's a dashed line right here that says bare minimum occupied hours, 67 per week. So that's this dashed line. Hopefully it's not too hard to see on your end, but these are run hours. So the building is running, the air handling unit systems are running longer than needed here. And then over here, it's running less than. And then once starting in June and July, then it starts coming more again. And this other dashed line is outside air temperature. So like what you'd expect to see is this range of outside air temperatures between 50 and 60. When it's mild outside, we should, you know, we should be at that bare minimum for minimally running the equipment. So the most ideal thing is like, which never ever happens, I never see this in the real world, is that because this is really hard to do, it's if you would actually configure the building automation system to be 6 a.m. to 5 Monday through Friday, just leave it. And then if there was working optimal start algorithms, it would be optimizing this extra runtime every day. So like the hardest thing, the optimal, it sounds really easy to do, but in reality, it's rarely implemented. If you're a facilities manager out there and you know that your building is optimized like this, like, you know, like hats off to you. I never see this. It's very, 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 very rare. It's a really hard algorithm to um, just set it and forget it. It's one of those that if you someone needs to be kind of like in this manner. What we're doing is maintaining it. It's some building automation manufacturers have the algorithm built into the building automation system for optimal start, and then in research, like Pacific Northwest National Labs has about there's research out there on the different kind of mathematics on how to calculate recovery rates. So that's like upper graduate mechanical engineering theory. Um, it's really hard to get it right and then have it working right. You know, as the building ages, some people I'm sure like they set it up once, it runs for maybe a week or two, and then someone the ECMs get removed over time. That's just the way things work. That when maintenance staff, they blast away the energy savings opportunities because it makes their job harder. They get graded on comfort complaints. They don't pay the utility bills. The accounting pays the utility bills, so they don't even see that kind of stuff. And there's no incentive for the maintenance staff to reduce the energy bill in the building. There could be. I've never seen that before either. That if the maintenance staff was incentivized to reduce the energy bill in the building, they would probably do it. They would be probably be ensuring that the equipment only needs to run as little as possible. Like, I've always wanted to see this. If there was some organization that would buy their maintenance staff, like a Walmart gift card for every, something kilowatt hours reduced of equipment runtime or something like that. I bet there would be a lot more buildings with reduced equipment runtime, if maintenance staff was incentivized. Sad thing is they're just not. Um, okay, so boiler plant, we see this, we talked about this yesterday. I'm sorry if this is redundant. As outside air temperature goes up, boiler plant runtime goes down. It'd be just really interesting. What is the boiler plant running all the time? So in here we can see, we talked about this yesterday, there must not be any reheat going on in the building. Chiller usage is going up. Looks really odd to me that chiller is running in March and April and May when I guess it does show the outside air temperature even getting into 60s. And so this is upper Midwest United States. So like it does get really cold in the winters, snow, frozen lakes. And then this is that time period where it's like really beautiful weather for low dew point, low humidity. But as soon as you start hitting June, we get slammed with really high humidity and really hot weather rising up from the Gulf of Mexico. That's seems really odd to me that there's a chiller operating in this time period. Maybe this is stuff that could be reduced. And then we talked about this yesterday too. Is binning outside air, binning hours of outside air into buckets when the chiller is running. This is a normal distribution, so it looks kind of how it expects the data to look. Most of the data, the outside air temperature was in between these ranges from March to, I think it started on the time series chart started on March and it ended in July 3rd. Most of the data was in these ranges. In we recorded the chiller running by a pump status, logging hours of outside air temperature that the chiller is running. And then some of these do seem a little bit on the cold side for mechanical cooling. So these are direct. If the outside air temperature is between 50 and 55, We should try and reduce that mechanical cooling. This is direct electrical consumption here, and then even trying to get it below here, below 60 degrees Fahrenheit. In theory, you should try and be economizing. The most ideal thing you'd want to see is you start the chiller here, and then there wouldn't see any mechanical cooling here. No recorded hours of mechanical cooling runtime. Oh yeah, I think I forgot to show you guys this. Okay, so this is the air handling units. Talked about this yesterday. Duct static pressure sensor, discharge air temp sensor, building pressure, chilled water valve, fan, variable volume supply fan. This is a really old schematic. For one thing, it's looks to me like Niagara AX, kind of older building automation graphics. Mixing air temperature sensor right here. So this is return air. So return air from the building comes through, mixes with the air handling unit here. So return, and then this is outside air, and they blend together. And then usually the PID for the cooling valve will control to this leaving air temperature. And then if a free cooling is enabled by the outside air, which we've been talking about, these cooling dampers, these mixing air dampers will modulate to maintain sometimes the discharge air temperature set point directly, or sometimes it's a mixed air temperature. And there's also a space temp sensor. So we can see this in this graphic. Well, I guess like the systems are off. But space temperature is, so this should be an average space temperature sensing. So the air handling unit would have supervisory level logic, averaging the space temp sensor. Hopefully it's an optimized average. Sometimes we average all of the space temps, and then sometimes we, select, about 5 or 6 space temps to get averaged. So like we'll apply fault equations to mixing air temp sensors, space temp sensors, return air temp sensors, duct static pressure. And then we'll be also one to see if the chilled water valve is leaking chilled water, which would cause really low discharge air temp if the fan is on. It does happen. In aged systems, really old systems, these valves, they do get performance degrades. I've seen it once where there was an old federal hospital in the US where they changed their chilled water system from a closed loop chiller system to piped into a campus chilled water system. A big Big Ten school is right next door, so they piped into the Big Ten, it's University of Madison's chilled water system, and then ever since they did that, it really screwed up their chilled water system. They had all these contaminants in the chilled water system, and the story is that so many contaminants that it acted like a sandblaster in some of these old valve stems, and then it slowly caused a lot of the valve no longer has a seal. So when the pumping system pumps, the valve, it starts leaking chilled water. Sometimes I've even seen where they break, where the chilled water valve just gets, the little actuator on top just dies, and then it's just stuck in some fixed position. So that happens too. All right, so hopefully that makes sense. There's a building pressure sensor, so that would be used if economizing free cooling season, and then these are open 100%, the 100% outside air right here, closed on here, and then the return fan turns into an exhaust fan. So we're pumping the air full of building, which would pressurize the building. And then there's a pressure set point. So building space pressure is notorious sensor that never works right. And then sometimes there would be like a variable fan or something in the building, or a relief damper somewhere that relieves pressure. if you ever have noticed, I see this in restaurants quite often, is because restaurants usually have like a makeup air, um, like a big kitchen unit that pumps, kitchen hoods, exhausting for kitchens and restaurants, and then they need to make up air to keep the pressure stable. And if you ever noticed, like that classic restaurant, you just can't quite open the door, like you have to give that extra nudge. That's a space pressure problem. um, or the notorious shoulder season building where the door is blown open and someone has to go shut the door because I bet you $10 that there's an air handling unit on the inside where one of these dampers is not working correctly. Um, you know, okay, so one thing to note is this looks really odd. 50-degree set point on the air handling unit. Um, usually, uh, Usually that's 55 degrees by design. Um, and then it just looks odd that there's 50. So that's a red flag to me. Why does someone need 50-degree air? Um, they're compensating for something in this old building that's not cooling properly. So they're what will happen is some place in the building, like it could be one VAV box, or this building that has 40 VAV boxes. It could be like a whole wing or something like that. It's not meeting the cooling load. So this old air handling unit, maybe it's not pushing the amount of air that it should be. These fans get tired. There's belts, there's pulleys, there's a lot of mechanical apparatuses. This fan needs to be have a certain amount of static pressure in it by design to push air all the way where it needs to go down the duct stream, and then when that degrades over time from some faulty part somewhere in the mechanical system, they'll compensate. They'll just lower the whole, make everything colder in the whole air handling unit, which may work as a band-aid, but it'll cause excess reheat. Everything else that doesn't need that extra cooling will be having to reheat. So we kind of get into those scenarios of driving your car down the interstate with the gas and the brake. It's simultaneous heating and cooling. Hopefully that makes sense. Okay, I think I'm describing this good enough. Then I'm leaving no time for the analysis. So maybe this will be a two-part video. So let me just get back here. This is the chiller. Just two little air-cooled chillers. Nothing too fancy about these guys. Seems interesting. They have precisely the same supply temp and return temp, even though the chillers are off. Usually when some electronic sensor is measuring to the 100th of a degree, that there'd be some deviation in that. So here at least the outside air enable set point is 55. So that's pretty standard. What I was hoping for in this chart is like if you set this to 50, or I mean 60, this would be the set point right here. You do that, you're enabling, if the chiller system was set to enable at 60, and then it was locked in like that, we would see that data here. But I think this building might have some air in the local outside air temperature sensors. So that could be like if there's air in the local outside air temperature sensors, that would cause faulty, premature mechanical system starting, that kind of thing. Okay, so this is what the building automation system versus web weather. This is a histogram. This might need to get redone here a little bit. We had a better histogram before. So this is, yeah, the deviation. Building automation system minus outside air temperature. As a histogram. So let's think about that. So like you see some, I think this is telling us that the building automation weather sensor, local weather sensor, reads higher than the weather data from OpenMedio, the local weather station data. Just keep that in mind, I think. Okay, so then let's see if we can get into some. This is our data model. So AI puts these data models together, which I think everyone should be using AI to do data modeling because it's much faster than a human, and it's really daunting, boring work too. But then us, the humans, all we do is have to validate the data model. That we do see 2 air handling units, we do see a chiller plant, we do see 2 chillers, we do see all of our VAVs, which I think I have all of that data. So, and then we can even validate. So this is the rule cookbook. So the rule cookbook looks for these column names. And then this is the haystack tag. And then this is the raw point name in the CSV. And then these are the rules that apply to it. So fall condition 1, that's guideline 36. That's a duct static pressure 1. So I think you get the idea. We'll see that in a little bit. Have to have some of this revised a little bit, but I think you get the idea. Is like you'd be able to see the what fault rules apply to what haystack name, and then if it's present in the data set. So for a chiller, we get a supply return temp fault. Here's an electrical power meter. Like we might need to build a way to see exactly. Check out a VAV box. I can see the AI is getting confused on PID hunting. So we should be mapping that to every VAV damper output in every reheat valve. The reheat valve on a VAV box would control to leaving air temperature or potentially zone temperature directly. And the airflow damper would be some kind of like a PI PID or PI control to the airflow and airflow set point. Okay, so that's the data model. Run rules. Okay, so we have 51 rules here. Now it's running all of the rules. Streamlit has like this, ooh, that was fast. So Streamlit has that icon, looks like a little triathlon guy up in the corner. If it's crunching some numbers or doing something, the little triathlon guy's running. Okay, so supply. Okay, so this is what we have the most here is supply fan deviation from set point, fan command status mix match, economizing when outside air is unfavorable. It'd be neat if we could rank these maybe a little bit better. I should take some notes. Outside air temperature mismatch. Cooling valve leakage. Ooh. Well, okay, so let's see what it did pass on. Hydrostatic static pressure, mechanical cooling when economizer is available. Mixed air temperature sensor is above outside air and return air. Pit hunting. Outside air too warm to be free cooling. And then these are the rules that didn't apply to the data model. Some of them require a cooling coil, heating coil temperatures. For trim and respond ones require a calculated VAV request. So let's just look again like what it did. So cooling valve leakage, stale data. I think we've seen lots of, I've looked at the data set before and there is some like data was not updating really well. I'm not too worried about it because it could just be something about how the data is like captured. So I'm gonna kind of like kind of get not pay too much attention to flatlined sensor data or sensors that are reading out range, that, but we have the fault there for it. We did record a couple faults for that, fault hours. This is one where the outside air, BAS, outside air temperature versus open media fault. So if they are within, if they're not within 5 degrees of each other by default, that is when we throw, this becomes, we start recording it as a fault. If this is a Niagara system, I do have a Niagara widget that'll scrape from Open Weather Map API, and then you can get that web weather data right into the Niagara BAS, and it's pretty solid. Works pretty good. It's free too with a Open Weather Map API call. Low OA fraction, so maybe we can look at that. Supply temperature above set point of full cooling. Supply temperature above blend. I think I've also kind of noticed in the data just a little bit. Maybe we can look at this. It's like the air handling unit doesn't keep up with supplier temp set point very well. One of the air handling unit doesn't. Okay, so this is air handling unit 2. Let's look at air handling unit 1. Let's look at air handling unit 2. See, damper, outside air leakage, fan mismatch, duct static below. No, one of the air handling units did not meet duct static pressure very well. Some stale data. What it does pass, it's not high on duct static pressure. Mechanical cooling when econ is available, so hit hunting. So let's okay. So let's check the chiller. There's no way I'm going to be able to cover this, and was trying to do this in within an hour, but there's no way that's going to happen. Okay, so this is, let's look at chiller. I think we do have a couple of rules for chiller. I'm going to come back to the chiller. Okay, so let's go look at some of these fault detection plots. I don't think there's much I can do for the chiller here because there's I'm only looking at 2 sensors basically, supply and return chilled water sensor, and then validating like there's not any like the they're within tolerance of like what a chilled water sensor should be in, and then like a degree per hour changes. And then mostly what I'm concerned with is if the when the chiller starts, when the chiller stops, and then if it's running in low load conditions too much, like in March when we saw it, and then also how well it performs on design day conditions. Like if it's it would be nice if you had some design documentation. Like we don't know how big the chiller is, how many tons of cooling. I think it's an air cooled chiller. And then what would be like the design inlet outlet temperatures, and then does it when it's running in design conditions, which would be really hot, really design day conditions, do you get that 10-degree delta across the chiller like you would? Okay, so this is the chiller. There's going to be just so much data to look at. Chiller 1. So this must be when it's off. And then if we get down in this information, down here, this would be like when the chiller is running during the day. So it does get like a 10-degree delta across it. This must be when the chiller doesn't run. What does look like a little bit odd to me is that if the building runs 24/7 around this time period, because if we only want to run the chillers if the air handling units are running. So maybe that's another fault. I should go rerun the data that when the airside systems are running, that would be a demand on the chiller plant. That's when we would load delta T. Okay, so let's I think we did look enough at the air handling units. I'm just gonna go right to this RCX plots. So this is just very generic retro commissioning is what RCX stands for. So fault detection plots and retro commissioning plots. So in retro commissioning, like we just study how the building operates over time, which I was explaining on some of the earlier videos. It's the most ideal thing we'd be looking for is how the building operates in peak heating season, peak shoulder season for free cooling, and then another special reporting period during peak mechanical season. So like 3 periods during the year, and ideally we'd be reporting in all 3 of those phases. Okay, so this is like the ranked worst performing VAV box based on percentage of outside the comfort band of 70 to 75, percentage of time. So most of these do pretty good, but here's these guys right here, VAV 7, VAV fan coil unit 3. Like, I think if I was in the service department or something, I would just go on the next control visit for updates and just look at a couple of these, look at these top 3 for sure, and then if you have time, maybe check out these ones too. but this guy is 100% outside of that comfort band, and then these guys do very, very poor as well. Yeah, something's really off in this data. It's only I've noticed one temperature sensor reached a value of 1 constantly. And then this guy is really wildly. So this guy on average is 76 degrees. Minimum is 68, or else it's up to 85. 69 on this one's average, so it's barely below. Minimum is 66 and 77 degrees Fahrenheit. And these are flagged as outliers. And there's some plotting for this too. And then the ones with the little stars, those are flagged behind the scenes with Python crunching some numbers in the background for anomalies. And it flags these guys as outliers. Something behind the scenes here is also, this could be like a flaky sensor here too. Device. Of course, it's kind of hard to see exactly what sensor this is, this dashed line. Oh yeah, it looks like it's VAV3 and VAV7. You see right here, it's kind of hard to see in this. But yeah, a couple of these VAVs right here. So maybe in my little report here, I'll say like these 3 VAVs seem to be problematic. Plotly, you can just download some of the stuff. So, okay, so let's go to, let's just go to chiller boilers. I mean, air handling units. Oh, wow. Okay, so like we need this filtered for when, this is an update I'll have to do in Plotly. So I'll have to make an update to the app, but, air handling unit 1. So this is data as a scatter plot showing the outside air temperature from this entire weather for this entire data set. As we're seeing outside air temperature on this axis, and then the supplier temperature from the air handling unit is on this axis, and then we can kind of see if there's this is all over the map. Usually you'd want to see like some kind of like a reset, like when it's really cold outside, the air handling unit supplier temp would be warmer, and then we would show a general trend of it when it's outside. When we start to get outside air temperature here, that the outside air temperature would start. Usually we'd want to see a trend like this. I need to make a note that if we could not be filtering. There could be the possibility that we're not filtering it for when the fan is running. So we don't care when the air handling unit's off, which it might be showing a lot of this data here as that. So let's check out the air handling unit 1. Yeah, same thing, really messy. Okay, so I'm going to make a note to update that. You can download any of this data. So check out 1 for the oh, I know. To look at 2. So like this application does have some of these plots pre-configured in data model, all linked up to the data model. So that's the power behind it. It's like it programmatically has everything, um, linked for the data model. And then this is the boiler plant data. So this looks normal. So like boiler plant, 160, 180 degrees. The reset is all over the map though. Like this should also be filtered from when the boiler system is running. That the standard linear reset for a boiler system is you have it pumping out 100 degrees Fahrenheit and design, when you need it hot. And then by the time we get up to 50 degrees outside air temperature, we could, if it's a condensing boiler, we could bring it down to here. So we would see a nice little linear reset over here, but this is all over the map. So it's either there's not a very good reset strategy going on here, there might be a small one right here. There could be the possibility that these boilers are older boilers, older cast iron boilers that they aren't high efficiency and they can't condense. So maybe that is the lowest that they'll go is 150. I'm guessing that this is the reset right here. And then we just happen to see a bunch of noise of when the boiler system isn't running for whatever reason here. And then this is just, the boiler catching up. So that could be flagged as an energy saving strategy. Makes me think like I might go back to the air handling units because there's one more strategy to look at. Okay, so we could be using let's see. There's supposed to be a duct static pressure. All mixed temps already turned to all outside air dampers. Okay, so this is what I've seen here too, so this is the air handling unit supplier 1 and 2 supplier temps. And as you could see, like in this one graphic, where's the guy? So this, you can see this right here, this 50-degree set point. You can see that in the data. The other air handling unit appears to have a 55-degree. See what they do in the winter. So they do float them up a little bit, not by much. But for whatever reason, this guy, air handling unit 2, requires that much colder temperature. So like ultimately, like this is what you would normally want to see in the winter and not this. So like when we have to, if I would place money on it in the middle of March, that there's one zone in the building that requires cooling, and then the whole air handling unit system has to deliver 55-degree cooling air all winter long. This side doesn't. And then the whole reheat system has to make up this difference right here. If this is energy wasted by reheat system right here. So I think there's some, if I would write a write-up that there's, I think the outside air temperature sensors are off, and if it's a Niagara system, we can get free weather data from the web and reduce mechanical cooling runtime. And some of these resets seem really off. There might be a couple of VAV boxes that are flaky, a couple flaky sensors out there. And I am missing the box plot for, oh wait, maybe it's coming here. So, okay, so this is fan speeds. We did see a whole bunch of like the fan not meeting duct static pressure. so this is what I want to see. This is a box plot for this is a box plot of the air handling unit duct static pressure. So these are outliers right here, and then this is outliers right here, and this is percentiles. So 50% of the time, the air handling unit maintains 1.5 inches of duct static. Fans on. So they do maintain about 1.5 inches pretty well. Standard deviation, they don't drift very much. And yeah, so there is no duct static pressure reset. There's no temperature resets. There's no resets in the building for energy savings. There's lots of energy savings things here, and maybe a couple VAV boxes that need some looking at that we could see. This is all I have for today, guys. I'm frankly out of time, but like we don't have any metering here. So if we had electrical and gas metering, we could see that here. But I think like this, oh, there was a little bit for the chillers too, but I don't think that's worth looking at because um, they're just sub-metering the chillers. I think like in time we should study like a little bit more of the these fault detection equations. So there were some like if I have time, I might go back through here and then actually study a little bit more of like the fault detection on the equation. So maybe we'll do that tomorrow. And then I can show you this other feature of there's a pre-built fault detection kind of retro commission style Word document that gets cranked out of here too. So like the little web app will send you a Word document. So I just downloaded it right here. One for each system. So I guess I downloaded the boiler one. But it's supposed to give us a what's it supposed to give you? So it'll give you all fault equations that apply to that system, and then it's up to you to go through here, and then we could actually tune the rule. So like each we can actually take a sub snip or something, and if you want to put it in your report, you would just go download a snip, and then you would have to manually go back into that Word document and then just put the snip into that section of the report. So maybe we should do that tomorrow. I'm just plumb out of time for today, and then I'll try and get one or two of those little small things patched. So, but hopefully this is making sense. Let me know if you guys have any questions. But this is kind of it. This is turning into a massive Streamlit application. So like, and it's all for free. And then it's all, you just pull it from the GitHub container repository with Docker, run it on your Raspberry Pi. You can run it locally, run this application locally on your Docker desktop if you have Mac, Windows. And I think in time we should also study. So there is also an agent specification for software. So any AI agent can look at this, and it's blessed by the Fable 5 model that it can recreate it. So what I'm going to do in the next couple videos is aim an AI agent at this and be like, recreate this all in Rust. It's 5 coded. This example, it's working good enough. So we're going to pump out a Rust version for the official Open-FDD. So that's coming. And tomorrow, let's do the Word document. Maybe I'll try and look at that a little bit ahead of time. get a pre-built report. And I think that's it. So like, and then maybe sometimes we could go look at some of the Python code inside here. There's just, this is turning into a huge Streamlit application too. So it has all of the rules written in here, the same thing we'd seen on the Open-FDD expression room cookbook. That's what I need to do, is like the AI gets confused on what a PID hunting rule should look at. So like we'll do this a little bit in more detail, but it's trying to match it up by point name. So, but I'll put a little bit more agent context in here, is that a PID hunting rule should be applied to anything that has a PID on it. So that would be a cooling valve controlling to maintain leaving air temperature, supply fan PID, it's maintaining duct drag pressure, and then these economizing dampers are also controlling to maintain more than likely a discharge air temp and set point, or it could be doing something with mixed air temp too. But yeah, hopefully you guys are liking this. Another thing I see funny that's in here, I bet this is where a minimum position for ventilation used to be. So we should take a note in here too to see if there's any ventilation going on in here either. So yeah, okay, so we'll do that tomorrow. We'll try and do the docx report as well. So hopefully you guys are liking this, and I will see you guys tomorrow.